Hi everyone, here I am with another one. And I really wished I was there with you in person to introduce a new section of a completely new topic in this course that is vectors, and especially be able to physically act out and essentially put on a show for you for those who have not taken physics, who are seeing vectors like this, these arrows, for the first time, but I can't. So we'll have to make do. I'll do my best to be thorough, and the silver lining is because this is a video, you can go and check it out anytime you want. Okay? And so you've seen vectors before. We have dabbled with it when we were talking about position, speed, acceleration, such and so forth. So we'll do the introduction portion very quickly. But more so, my goal for today is to introduce two different systems that describe essentially the same thing. One system can be effective or efficient in one style or it serves a certain purpose. Another system also serves a different purpose. They obviously, as you can see, demonstrate or illustrate the same arrow, but how we use it, one system can be more useful than the other. Okay, we will practice a little bit of the geometric vector system and an algebraic vector system, essentially describing it in two different ways. We will talk a little bit more in depth about how to calculate the physical distance, or rather magnitude, of a vector or an arrow. And we'll do a little bit of, I guess, geometric, spatial, visual manipulation so that you understand what a vector actually is in a 3D space and how it can be used. Your goal is to be super comfortable with these arrows and what they mean. And from there, yeah, we start to blow it up. It will, for better or worse, blow up in your face a bit. And so please dedicate today to really doing every question in the homework. All right. Without further ado, I am going to go on. Just like before, I am going to ask the substitute to pause here and there so that it gives you an opportunity to take a shot at it. And if you're wrong, you're wrong. But please try to participate when I prompt you to try these practice questions based on what we talk about. Okay? So here we go. A vector essentially is not just a number, but a number and a direction. Okay, a vector has some kind of quantity and some kind of quality. You already know that. So in I guess up until grade 10 science or grade 11 science, in physics, you would have talked about mass, a distance, and even a speed. However, when we add a direction to this mass, I should, you know what? That's a misnomer. If I apply a certain acceleration, a certain movement, I suppose, and turn it into a force, it would be, it would include a certain direction down. If the distance was given a certain direction, it would become a displacement. If I gave a speed a certain direction, it would become a velocity. In other words, scalar, a certain number, becomes a vector when you give it a direction. That's essentially it. So I guess what we're trying to introduce here is, in a vector standpoint, every single quantity has to have some kind of quality. And so if you don't, you're missing something. Okay, consider this. Here it is. So we have vectors are generally described in a start and an endpoint. So you can say that this is your start point, like A right here, and the letter following would be the endpoint right here, right? Yeah. Another way we describe the start and the end is the initial and the final. Another way we describe it is as if it was an arrow, so the A would be the tail and B would be the tip or the head. Depending on what textbook or even what teacher you describe, there is something that we introduced in 6.2 called tip to tail when you're adding. And so, yeah, instead of a head, we can technically call that a tip. And literally, what I mean by the arrow is you can pretend that this is an arrow and, you know, it's flaming, it's burning this way, right? That's a sweet arrow, you might say. Okay, and it's going in that direction. And so we have A, B, and it describes a vector by having a little arrow on top of it. If I just wrote AB, or even AB with a line across it, that is a universal symbol for a line segment. Okay? If you want it to say it's an actual direction, it's got to have an arrow on top. Just little semantics. I hope that makes sense to you. Another way we can describe it is an algebraic. So as opposed to saying, here's my start, here's my end, this is in 3D space with no real sense of direction. So if this was literally a spaceship in space, like here's the Earth, round, okay, here's the moon, here's Mars on the way, and then here's like Jupiter and then Saturn, like whatever. There is no up, down, left, or right. It's just some arrow in space. Okay, and for the sake of mathematical calculations, that's sort of useless to us, right? It paints a picture, but it's a little bit tougher, I guess, to calculate right away. And so why not introduce some numbers? Geometric vectors can be written as algebraic vectors by pretending the tail of your vector is located at the origin 0, 0, or just some reference point. So if I say vector AB has a components, or has a component of 3 comma 4, just like how you would write an ordered pair of xy, the components describe how far in the horizontal direction we move, plus how far in the vertical direction we move, to create a vector of 3 comma 4. Okay, it's pretty self-explanatory, or intuitive rather, and so don't think too hard about it. If you see a vector AB described in square brackets, really important, square brackets, as 3 comma 4, that is not a coordinate, that is a vector. It describes the horizontal component and the vertical component. Okay, I hope that's good. So let's try these two systems. All right, so here's where the substitute teacher, if you could pause the video as soon as I explain, it says draw displacement vectors of PQ, remember order is important, PR, and RQ. Okay, and here, draw position vectors from the origin 0, 0, that's right here, to vectors A, B, and C, write each as their component, which means you're going to have to count. Okay, let's try it. PQ, PR, RQ. If the substitute teacher could pause for 30 seconds exactly, shouldn't take more than that, and go. Okay, assuming that you've done it, we have PQ, so it's P to Q. You would have to have drawn it this way if you wanted the vector to be correct. Okay, this is PQ. PR would now be this way. If you drew it the other way, you would be incorrect. And if you drew RQ, it would be like that. Okay, so this is RQ, and this is PR. You might be asking, well, what does happen if you draw it the other way? Well, you'd have to write it as RP. That would be the correct way. In 6 point, actually, at the end of this lesson, I do introduce how you could change the direction of a vector by sticking a negative in there, but that requires some multiplication of -1 business. So let's talk about that later. Okay, just stick to it. Start and finish, start and finish. You might ask, Mr. Kim, what's with that funky thing? That's something that my grade 13 teacher taught me when I was a kid. It's just a slang or just a quick way of drawing an arrow. Some textbooks actually prefer that because it's, I don't know, it's just short form. You don't have to do that for me, okay? But me, with my messy writing when I was a kid, drawing like this and drawing that was taking up too much space. Like, I didn't want to draw that piece. So don't think too hard about it, okay? It's up to you. Next, drawing all position vectors from the origin. Okay, simple enough. O to A, O to C, and O to B. I will label this. This would be OA, OC, and OB. Notice how the O comes first and the letter corresponding comes second. Write each as their components. Okay, vector OA would be 1, 2, 3, 4, comma, up 4. Okay, this would be 1, 2, 3, 4, 5, 6, comma, 0, and this would be 6, comma, 1, 2, 3, 4, 5, 6, just like that. Okay. Yeah, so components super useful when we apply a grid. We have a reference point. It's a lot easier to describe. But geometric vectors have their extremely good uses too, so don't underestimate that. Let's continue. Please turn the page. Magnitude. Magnitude is also very intuitive. I'm literally asking, hey, what's the distance between here and here? And you might have guessed, when I draw the horizontal and vertical components as dotted lines, it creates a 90-degree triangle. And how do we find the side opposite of a 90-degree in a 90-degree triangle? Pythagorean theorem. That's right. Magnitude of a vector is denoted by its absolute value. Now, when I do the Pythagorean theorem, you would see that the vector's distance or magnitude is always going to be positive. There's two different reasons. I could talk about it in a mathematical perspective, but I want to talk more about just literally the word magnitude. Magnitude, in other words, I don't care if it's a positive 5 or a negative 5, that is a distance of 5 away from the value 0. Like absolute value. Okay? So let's try it. If I had the magnitude of vector v, how would I start with? Just vector v is going to be 3 and 4. Right? The magnitude, though, is a little different. You can't just say 3, 4 and expect it to be done. Vector is going to be the magnitude of the square root of 3 squared plus 4 squared, and that would be 9, 16. The answer would be plus minus 5, but it's the absolute value, so it's just going to be a 5. Okay. If you're wondering how the heck did I get this, please remember the magnitude of v squared is equal to 3 squared plus 4 squared, thanks to Pythagorean theorem. So square root both sides, and I get this. Okay, I'm just taking your understanding of this for granted. Now, please also note, because it is a component, and I'm doing absolute value, I actually don't care if it's this way or if it's this way, or if it happens to be this way, or if it happens to be this way. It's like the same magnitude. I do not care about the direction. 5 is a scalar value. So we say its magnitude is denoted by the absolute value without the vector arrow. The magnitude is a scalar quantity. So this, I can simply write it as v. Okay. All algebraic principles can be used freely, such as the Pythagorean theorem. AB can be expressed as square bracket 3 comma 4. The magnitude, which is just v, is equal to 5. Hope that makes sense. Let's practice our Pythagorean theorem. Everyone, looking down at the practice section, I'd like you to quickly draw each of these vectors, and using this chart, please calculate the magnitude of those vectors as well. If the substitute can pause the video, and go for it. Okay, once again, assuming that you have paused and you tried it, this is O with A, this is A with B, and that is B with C. I'm going everywhere here, okay? But in fact, since I am looking for the magnitude, I really don't care about the direction, okay? OA is, let's see, -2, comma, 2, close square bracket. The magnitude of OA is going to be, well, OA squared is equal to -2 squared plus 2 squared. That's going to be 4 plus 4. The absolute value of the square root of 4 plus 4. Now at this point, I did make a quick error. I should add absolute value here because the absolute value is there. Okay, so the answer to this is going to be plus minus root 8, but I don't care about positive or negative. It's just the magnitude I am interested in. Under that same principle, AB. Okay, AB, please don't be confused. It is still a component that is moving to the right by 1 and 3 down. You might be thinking, what are you talking about? Isn't it supposed to be from 0, 0? I understand. But remember, the vector simply needed a reference point. So if we use reference point of 0, 0, and I did this arrow, wouldn't you agree that this black arrow and that blue arrow of AB are identical? Now, I know that they are different in where they are located. However, are their directions the same? Are their magnitudes the same? Yes to both. And so vector AB is identical to vector OP. You get what I'm saying? And so I can pretend that this blue arrow starts at 0, 0 if you wanted to, and count down, and that is still the vertical and horizontal components of vector AB. Okay, so I'm going to take this and say my horizontal component is a positive 1, my vertical component is a negative 3. Vector AB can be described as 1, negative 3. And with that said, the absolute value or the magnitude of vector AB would be absolute value, the square root of 1 squared plus negative 3 squared. The answer would be positive square root 10. Okay, so same thing here. Let's do this. Horizontal 1, 2, 3, 4. Vertical 1, 2. Vector BC can be described as 4, 2. The magnitude of vector BC is the magnitude of the square root of 4 squared plus 2 squared. And that would be a positive square root 20, a scalar value. And that's vectors. Right? I'm going to push it a little bit. For example number 2, I am going to do it together because it might be a little new and a little shaky. I don't want you to feel like you're sort of thrown in trial by fire. But you will do number 3 for me by yourself, okay? So pay attention. Consider cube A, B, C, D, E, F, G, H. That's my cube, with side lengths equal to 10. So I'm just going to write this distance right here is 10 centimeters. Find the magnitude of the following vectors: A, B. So I shouldn't do that. Since it's a cube, I can assume every side length is identical. So vector AB is going to be 10 as well. Easy. Vector BD, however, vector BD. Vector BD happens to be a hypotenuse of a right angle triangle with side lengths 10, 10, ta-da. So if you're looking at vector BD, the magnitude would be the magnitude of the square root of 10 squared plus 10 squared. So that would be positive square root 200. Right? BH. Okay. BH. I'm not sure if that is a little trippy. So what I'm going to try to do is manually draw something in 3D. BH is going to be like, does that work? I don't know. That's terrible. Let me give me one more shot. Give me one more shot. Does that work? I'm trying to. Oh man, I suck at this. Okay, but you get the point. BH is from the corner closest to you and shooting diagonally through the cube to the corner furthest from you. So you got to visualize that. So there's a big element of spatial visual awareness that comes with vectors. So let's try it. BH. How in the world are we going to calculate that distance? Well, if you think about it, there is another right angle triangle involved. What is that? Well, imagine this is B. B connects to D, and D goes down to H. B to H is actually a hypotenuse of another right angle triangle. It's right here. It's 3D, right? And so I know what BD is. The distance is square root 200. I know what DH is because that's the side length of a cube. What's the magnitude of BH? So as you can see, I am actually applying regular standard like algebraic principles that we have learned a long time ago. So we've got the square of BD, which is 200, plus the square of 10, which is 100. So the Pythagorean theorem says BH, the magnitude of BH is positive 300. And there it is. So considering that is the case, once you are ready, I'd like the substitute to pause once again and please try number 3. And for this one, how about we give it just under 5 minutes? There's 3 different vectors that I like you to explore. So just 5 minutes, no more, and see how much you can figure out. Let me read the question for you. Consider a regular hexagon, A, B, C, D, E, F. The center is O. The side length is 2. So that's a 2, that's a 2, that's a 2, so on and so forth. Find the magnitude of the following vectors. AB, AB. Find the magnitude of AC. And then find the magnitude of AD. Okay. So there we go. If you could pause the video, please, and no more than 5 minutes. Go. Okay, let's try it. AB, very simple. It's one of the side lengths of the hexagon, so that's a 2. AC, however, starts getting a little bit tricky. I mean, I can probably figure it out because I know how to manipulate vectors. But for you, as far as I know, all you know is how to manipulate triangles. So what you're going to have to do is consider this is a isosceles triangles with side length 2, 2, and you're looking for that length AC right there. Okay, so what do? I don't know. But there are some geometric principles that can help us. Geometric. This is a hexagon. If you remember a hexagon, you should be able to calculate the interior angles of a hexagon. Now, If you don't, you could also consider that these are all equilateral triangles fit together. Remember when you were in kindergarten? There were those puzzle shapes that had like these things. They had rhombuses, they had parallelograms, they had trapezoids. You know what I'm talking about. Okay, red, yellow, blue, white, that kind of stuff. Everyone had that. There was also a green triangle shape. And you knew that one yellow was equal to 6 green triangles. You know that's the case. Okay? If you wanted to go a little further, you remember in grade 9, you were able to calculate the interior angle of any polygon, and that was the number of sides of your polygon minus 2 multiplied by 180 gave you the total angles all around. And since I have 6 corners, I would have to divide by whatever that was. So that would be divide by 6 or divide by n. Okay. And in this case, n minus 2, that's a 4, multiplied by 180, that's 720, divided by 6. Each interior angle is 120 degrees. Okay, so this is 120 degrees, which also tells you that this is 60 degrees and that is 60 degrees. Which makes sense because these are all equilateral triangles. They have 66, 60 adding up to 180. Now, that's not important. If this angle is 120 and it has to be isosceles, right? You have these two angles, you have that angle, you have these two sides. You could do a whole bunch of stuff. Since I don't want to do more calculations, I'm going to use cosine law, side, angle, side, and say, okay, my mystery side, well, magnitude, squared is equal to other side squared plus other side squared minus 2 times the one side times the other side cosine of the contained angle. And that gives you some number. Let me use my calculator. And once I calculate that, I square root both sides, and it seems to me I get root 12. Big whoop. But hey, know that there are ways around it, okay? All the previous geometric and algebraic principles are coming into play. Now we get to AD. Oof. What can we do about it? Well, I'm actually going to cheat. I'm going to use AC. AC, this line right here, and CD, right there, will create a 90-degree angle. So I'm going to use that and just use Pythagorean theorem. How do I know that? Well, remember, if this is 120, that's a 30, and that's a 30. I also know that because this is part of the equilateral triangle, that's a 30. And since this is one corner of an equilateral triangle, this is 60. Together, it makes 90. Okay, so side AD is going to be Pythagorean theorem, the square root of the distance of AC, which is root 12. So that's going to be squared as a 12, plus the distance of CD squared, that's going to be a 4. It is positive square root 16. Oh, perfect, which is a 4. Wait a minute. Is there a special relationship? I think so. Take a look. This is the length of one side of a hexagon. Wouldn't you agree that this is exactly 2 of those lengths? Hey, 2, 4. There's a reason for this, and I will get to it in 6.2. You won't ever have to do this stuff again after we learn how to add vectors together. But for now, keep it at that. Here is a full rundown of how to manipulate or calculate and determine magnitude. And it wouldn't be a full lesson if we don't get to direction. So let's talk very quickly. I'll only say this. Direction makes your scalar magnitude into a vector. So magnitude and direction together makes for some interesting statements. Consider this. Vector AB, in other words, going this way, and vector BA, going this way, are opposites. But their magnitude is the same, right? Vector AB magnitude and vector BA magnitude, because I don't care about the direction, I only care about the distance. So since their direction is 180 degrees of each other, the vectors are not the same, but instead, you can say, if we change the direction, then they are fully identical. Okay? In other words, consider this if you've never worked with vectors before. When a vector v is defined, the opposite vector can immediately be denoted as a negative of the previous vector. Note that the location of vector does not matter, only the magnitude and direction, just like I was saying before. Number 2, this is pretty cool. Parallel vectors like AB and CD. AB, so AB, BA, CD, and DC are all parallel. They have the same or opposite directions, not necessarily the same magnitude. So parallel is a keyword that tells you something about the vectors. Okay, so not the same magnitude, but same or opposite direction. Not even the same direction. It's same or opposite direction. Okay, so here we go. Yeah. So with this in mind, equivalent versus and parallel, I'm going to ask you a couple of questions so that you're forced to use a negative in front of the vector, a -1 in front of the vector. Okay? Practice. Using the hexagon once again, please identify 3 pairs of vectors that are the same, opposite, and parallel. Okay? Let's see. 30 seconds, 30 seconds. No more than 1 minute and 30 seconds. If the substitute could pause and go. Okay, assuming you tried it, here are 3 equivalents. You can say FE is identical to OD, which is identical to AO, which is identical to BC. Okay, you could have also said, let me use a different color this time, because everyone's answer could be a little different, right? You could have said EF is the same as DO. That also is the same as OA, which is the same as CB. As long as you are choosing one and keeping it consistent, you're fine. You don't have to go in that direction. You could say EO was the same as DC, which is the same as OB. I think you get the point. Okay, you get the point. You get the point. What are opposites? Well, for the sake of not messing up this picture anymore, all the blue and the reds, they are opposites. They are equal distance or equal in magnitude, but opposite in direction. That's what opposite is. It can't be longer. Okay. Just to, again, opposite means magnitude is the same, but the direction is not. Okay, just because the direction is opposite doesn't mean that they are opposite. Okay, if they are opposite in direction, but the magnitude is not the same, they're just parallel. If you state that it's opposite, it implies that the magnitude is the same. Please make sure you know the difference. So these are in fact parallel, opposite. Okay, parallel. Well, EF. So the blues and the reds, they are all parallel to each other. But I have to add another layer to this. Remember what I just said? If they are parallel, magnitude won't matter. So I could say, what am I doing? I could say AD, which is twice as long as the others, is still parallel. And DA is also parallel to all the blues and greens, all the blues and reds. It doesn't matter what the magnitude is. Okay? And that does bring us to the end. There's so many homework questions that you can do, but just in case, because the textbook does start using different direction systems, I wanted to go through them and give you some examples of how it's presented. There are three that I'm going to discuss. One is true bearing or azimuth bearing, and it is when you use a full 360 starting from the north direction. So if I gave you a vector that is vector u, it is 135 degrees from the north direction, and it has a magnitude of 2.3 kilometers, you would say vector u equals 2.3 kilometers, okay, 135. And please note, it has to be clockwise. Like if I had a vector here, I can't do this. It has to be clockwise. Okay? That's why we say 135. And the same point, vector v has a magnitude of 2 kilometers with a bearing of 060 degrees. I am not sure if the 0 there is mandatory. I feel like it's redundant, but I'm going to keep consistent with what I have learned and what the textbook does. Okay? You could investigate and teach me if you want. Quadrant bearing, a measurement between 0 and 90 degrees east or west from the north or south line. So these are the two same vectors, but if we use quadrant bearing, we are dividing 360 into 4 different pieces, and we must either start from the north and rotate, okay, rotate, or you will start from the south and rotate, and you will use numbers that are within 90 degrees. So here I have 135 degrees as true bearing. How would I describe that? It is a smaller angle underneath. So what I would say is angle U is 2.3 kilometers, but from the south direction, we rotate 45 degrees to the east direction. Okay? So from, and this one is towards. Okay? Let's try this one. Vector v is, I'll give you a chance in 5, 4, figure it out, 3, 2, 1. It would be 2 kilometers from the north direction because it's closer to the north than it is the south, and we rotate 60 degrees to the east. Okay, there it is. Lastly, sometimes, like geometric vectors, it is unspecified. Sometimes we will simply say it is an angle from some arbitrary reference, such as the horizontal, or from another vector itself. That's geometric, because we don't have numbers or a Cartesian coordinate to use as a reference. So here it is. Angle from the horizontal. Vector PQ would be 14 centimeters rotated 110 degrees from the horizontal, north of the horizontal. So I'm not going to write, I think I'm going to type it out. Ready? Is 14 centimeters rotated 110 degrees. And I might have forgotten how to do the alt code for degrees. Let me see if I can figure it out. Alt 0183. No, not working. Anyways, 180 degrees counterclockwise north of the horizontal. So you have to have specified a lot, right? Because if I just say 110 degrees north of the horizontal, I suppose that would work. No, being more clear, I think, is better. Here's another example of why it might be a little frustrating and why this is not often used. Let's see. 5 kilometers, vector BC. So notice there is no C here, but vector BC extends, in other words, tail to tip, extends from B and goes to C by rotating 60 degrees clockwise from the direction of vector AB. What is this describing? Well, the direction of vector AB is here. Right? That is the extended vector AB. Vector BC from B, it will rotate 60 degrees in the clockwise direction. And so it would be something like that. That would be C. You might be asking, where's the magnitude? You're right. There is also another typo. Let's pretend vector BC of magnitude 1 kilometer. Okay, so that would be 1 kilometer. So if I wanted that to be scaled, I would have to make this very small. 1/5 of 5 kilometers. So it would be something like that. Okay, so again, it's not the clearest system, but if I were to write something out like this, you should be able to navigate to a degree. And I think there are some practice questions that do get you to work on that. I forget. I do know for sure, though, that the true bearing and the quadrant bearing are very popular. So please practice that. All of today's homework sheets are going to revolve around getting really comfortable with vectors. Those of you who have done physics will see this to be very boring or very repetitive. Do it anyways, and we are going to start manipulating these vectors with the assumption you have this practice down. So work hard today. All right. So farewell. I will see you tomorrow.